All right, so we're going to complete this problem review for chapter 17. So question number 7, let me read it again. It says, using the data shown in the figure 17.7, calculate the greatest distance at which a star like the sun could be seen with binoculars, and so forth. All right, so we're going to do each of these. The basic idea here is we're just using over and over this equation. The distance, if you know the apparent magnitude and you know the absolute magnitude, you can calculate the distance using this formula. That's really all it is. And so it's 10 raised to this power. Okay, so it's the power, and you got to do what's in parentheses first. So it's the apparent magnitude, that's the little m, minus the absolute magnitude, that's the big M, plus 5. All right, and then so you figure out what that is, and then you divide by 5, and then you take that answer, and it's 10 raised to that power. All right, so here's some examples, right? They said the first one is with a pair of binoculars. So with a pair of binoculars, they tell us that you can see to an apparent magnitude of 10. And of course, the sun has an absolute magnitude of 4.83. So that's important for all of these problems. We're going to keep using that. Remember, that's the magnitude that a star looks if it was 10 parsecs away. All right, so that's just a number that we're going to use for all 4 of these calculations. So it's 10 raised to this power. So do this part first. 10 minus, this part's really trivial. 10 minus the 4.83 plus 5. All right, and so calculate what that is, and then divide by 5, and then you take that answer and you say 10 raised to that power. So when you do that, it turns out to be that with a pair of binoculars that can see an object that has a magnitude of 10, you could see the sun, which has this absolute magnitude, could be seen from 108 parsecs away. All right, so let's do B. So with B, it says, let me look at it real quick, with a 1 meter telescope. Okay, so that's actually a fairly large telescope. They're talking about the opening of the telescope, the diameter of the opening. Anyhow, so I'm using the lower limit that they actually gave, a range of so let's say it's, somewhat the poorest possible quality of that 1 meter telescope. So they tell us that you can see, an apparent magnitude of about 18. All right, so just 18 minus the apparent magnitude of the sun, which is 4.83 plus 5, and then you figure out what that answer is, and then divide by 5, and then 10 raised to that power. It turns out that you can see this. So it's 4,305. That's a 0 right there. Sorry, it's 4,305. All right, and then let's do the next one. All right, so this one they say a 4 meter telescope. So the distance would, and so you look up in that's the little figure 17.7. You can look up a 4 meter telescope. You could see an apparent magnitude of 26. So it's pretty dim. That's a very, very dim object. Anyhow, so it would be 10 raised to the so it's 26 minus 4.83 plus 5, right? And so that turns out to be 12.7. So that's what's in parentheses right here, the 12.7, and you divide by 5. And so that would be, so really this is just to tell you what this looks like in a little bit more detail. So this becomes 10 to the 2.434. All right, so you raise 10 to the 2.434. All right, and so let me do that in my calculator. All right, and here we go. So let's see, what does that come out to be? Come on, where's, oh, sorry. Okay, I shouldn't try to type into my calculator while I'm recording this. I'm sorry about that. So when you do this simple calculation, it turns out to be, it's 10 to the 5, whoops, let me change this, 10 to the 5.23, 234. Okay, so 10 raised to the 5.234, all right, so it's quite different than what I had before, sorry about that. All right, so the distance turns out to be, it's enormous distance that you'd be able to see a star like the sun. So it would be 171,395.7 or something like that, 0.7 parsecs. All right, so that's how, you'd be able to see that with a 4-meter telescope. Remember the sun has an absolute magnitude of 4.83. All right, so let's do the last one. All right, so part D is using the Hubble Space Telescope, which of course, is this incredible instrument that we've used for a long, long time now. So with the Hubble Space Telescope, you can see things that have an apparent magnitude of 30, which is unbelievable. All right, so it's 30 minus the absolute magnitude of the sun plus 5 divided by 5, and so that would be 10 to the 6.034. So when you do that, you get over 1 million parsecs. So 1.08 times 10 to the 6 parsecs. So over, that's well outside the galaxy, by the way. All right, here's, again, what we're going to do is the exact same formula, but this is to estimate stellar lifetime, okay? And so the equation is, if you know what the mass is in solar units, and you know what the luminosity is in solar units of some star, it's the mass divided by the luminosity times 10 billion, right, which would be 10 to the 10th years. All right, so let's do this first example. So they give us a star that has a mass, a much smaller star than the sun, so this would be, like a red dwarf. So 0.2 divided by 0.01 turns out to be 20, and then times 10, times 10 billion would be 200 billion, right? So this would turn out to be 200, right? 200 times 10 to the 9th, or you could write it in words, 200 billion years. Okay, so that's, that would be the age of this star, 200 billion years. All right, let's do the next one. All right, so for part B, they give us a star that's has more mass, 3 times the mass of the sun, and has a luminosity 30. So it's the luminosity is 30 times that of the sun, and so when you do that, notice this fraction is of course less than 1, so you multiply this times 10 to the 10th, or 10 billion, it's the same thing. So you get that this star would only last 1 billion years, right? That's what you could write it in words, 1 billion years, or 1 times 10 to the 9th, right? And then we get to the last one. It says, okay, so what would be the lifetime of a star if it had a mass 10 times the mass of the sun, and its luminosity was 1,000 times the luminosity of our sun? So you do that, and of course, you multiply that fraction by 10 billion, which is of course 10 to the 10th, and so you get, now this star doesn't even live a billion years, right? Its entire lifetime is 100 million years, right? So, all right, so is that it? Yeah, I think that's the last one, right? So that's and they said that one's what's called a blue giant. So notice the red dwarf, right? This tiny little star that had a mass of 0.2, part A, 0.2 times the mass of the sun, and a luminosity much less than the sun. It lasts a whole lot longer, right? Much longer. And remember, for part A, it was 200 billion years. Keep in mind, the universe, the age of the universe, is 13.8 billion years. Yeah, that's actually important to understand that. So the age of the universe is 13.8 times 10 to the ninth years. Right, so that's the universe, right? That star will last, well into the future, right? So, All right, so that is it for chapter 17. Let's stop this. Where's my mouse?